Hi, and welcome back to R for BRFSS. I'm Jennifer, your instructor for this tutorial series. We are now in the third and final chapter of our segment on market basket analysis. In the first video, we read our article and subset and cleaned our data file. Then we did some data analysis using the a priori algorithm. Finally, we're going to interpret our findings compared to some basic simple descriptive statistics. So I have not closed my R session over these three videos, so I have everything already on my R console. All of our data files are a priori. The results from our a priori algorithms are all right here. So what we've been talking about in these association rule minings are trying to figure out what comorbidities exist for male and female respondents. Right, because we have the sex of the respondent on the right-hand side of the association rule, and on the left-hand side, we have their disease conditions. So when you have multiple disease conditions, that's a comorbidity. What we want to do now is kind of, we have all of these association rules. We can see that there are a lot of comorbidities. Even having looked at prevalence estimates in the last segment, our last tutorial segment, we know that a lot of individuals have at least one disease condition, but the question is how many people have multiple disease conditions, and what does that distribution look like across the population? So in order to kind of explore that a little bit further, what we want to do is create a new row on our data set called CG17DM. Let's just glimpse that. We want to create a new column on this data set that takes the sum of all the comorbidities. So we want to count the number of comorbidities. The way that we do that is by calling rowSums. So let's call this CG17_DM $. Let's call this new column comorbid. Put the assignment arrow, and then take the row sums of CG17_DM for the columns 2 through 15. 2 through 15, because our first column is a sex variable, so we don't want to take the sum over that, but we want the sums of these columns. So for each individual, so for each row, we want the sum of these columns. So this is rowSums. And let's run that command. And R can't figure out how to do that because we've set all of our variables to factors. So it can't take the sum across a set of factors. So what we can do instead is we can do CG17_DM, let's call this new data frame 1, and we can set a command over the entire data frame to apply to our CG17_DM the as.numeric commands. So let's go over that. So we're creating a new data file called CG17_DM1, which is which applies to our data frame using this sapply command on the original data frame CG17_DM to set all of these variables as .numeric, so 2 numbers. We run that. Now let's take a glimpse at our CG17_DM. And, CG17_DM1. And we see now that it recognizes them all as doubles, which in the glimpse function, double means number. But look at this. Now we have 2's in here, 2's and 1's, where before we had 1's and 0's. So this is problematic. I'm not really sure what happened in this command, but it changed all of our zeros. It changed all of our 0's to 1's and our 1's to 2's. So that's a problem for us because we want to take the sum of the health variables where the answer is 1. So we want to add up the 1's, not the 1's and the 2's. So what we would have to do now is recode these values back to zeros and ones, which is kind of dangerous because right now we're looking at about 40 observations and we don't know what's in the rest of the data file. So by glimpsing, we can assume that zeros are ones and ones are twos, but we don't know for sure. So it would be dangerous to recode. But also, because we've been working with the arules package, that package, let me show you. When you load the arules library, it does something to some dplyr functions. So the following object is masked from package :dplyr recode. So we've been recoding our variables using this recode command from dplyr, but when we install the arules library, we can't use recode anymore. So if you want to recode your variables, you can't do it during this R session. You would have to close out R and then not load your arules library, and then you could recode if you want to. But that's getting to be too much work. So what we're going to do instead is take advantage of the data loss that occurs when you export a data frame out of R to a CSV file. So let's call our real library, and let's export cg17_dm, and we'll call it cg17, oh, we have to put quotes, cg17_dm.csv, quote. All right, so let's open that data file, cg17_dm, and it looks good. We have all of our zeros and ones. Here we see that we have possible data loss, which in this case is to our advantage, because when we read this file back in, R will forget that these are factors and it will read them as integers. All right, so let's import that back in. Import, parentheses, quote, cg17_dm.csv, quote, parentheses. Okay, what I meant to do is set this to cg17_dm, assignment arrow, import that, and now let's glimpse cg17_dm. So now you see all of our health variables are identified as integers and not factors anymore. So now we can use that callSums function across this data frame. So let's now create our new comorbid column. So cg17_dm $comorbid. This just attaches the comorbid column to the end of our data frame. Assignment arrow. We want to do the, what is it? So rowSums of cg17_dm. Keep all the rows, but just take the columns 2 through 15. And now let's glimpse cg17_dm. And you see we have this final column, which is identified as a double, which is a number, as.numeric. And these are the number of comorbidities that each survey respondent has. So the first person has 8 comorbidities, the second one has 4, 2, 0. All right, so now we're going to just do some basic descriptive statistics on this final comorbid column. We're still looking at the differences between men and women though, so first let's create a new object that contains only our female respondents. So cg17_dm, then put a pipe, filter where the sex equals F for female. Now let's look at, let's also set our object for males as well while we're at it. cg17_dm, then the pipe, filter where sex equals M. So now we have our male and female data sets respectively. We can look at the mean of the F comorbid column, And we see that on average, female respondents had 1.78 comorbidities. Let's look at the mean for the male comorbid column. On average, males had 1.83 comorbidities. That actually is kind of surprising to me because when we were looking at the association rules, female respondents had about twice as many association rules related to their comorbidities than did men. So this is interesting. Let's check out the median for female comorbidities is 1. The median for male comorbidities is 2. So we're seeing again that men, in general, men have a greater number of comorbidities than women. So let's look at this on a histogram of comorbid. And I'm going to save this figure in our history so that we can refer to it after we call the histogram for $$ comorbid. Okay, so this is our histogram for the number of male comorbidities. Let's also add it to the history. And now let's page up to look at females. So female, male, female, male. The distribution kind of looks the same. They're both highly skewed to the left. But what I want you to notice is that the number of males with 0 chronic disease conditions or 0 comorbidities is, this might be, I don't know, 2,300? 2,300, but for females is 2,500. So there are more females with 0 comorbidities than there are males. There are also more males with 1 chronic disease condition, so this might be 1,100, and we look at females, this might be 900. So there are fewer females with a chronic disease condition compared to males. Same thing if you keep looking stepwise down, males just have more comorbidities. And this difference in the frequency is not because our male sample size is so much greater than our female sample size. So if we count our females and count our males, they're really about pretty well evenly distributed. So 4,700 versus 4,500. So this difference that we're seeing in the histograms and in the median and the means is not attributable to a difference in the number of survey respondents. It's really attributable to the differences in the number of comorbidities per male and female respondents. So what does this mean in comparison to our association rules? Let's call our association rule results back into our console. So I want to look at female on the right hand side, support 0.001, confidence 0.5. So let's look at that. And I also want to look at men on the right hand side, support 0.01, confidence 0.5. So we're just calling our association rules back up to the R console. Okay, so look at this. This is for sex equals M, so this is for male respondents. The longest association rule, so the greatest number of comorbidities in these association rules occurring for 10 survey respondents who are male is 1, 2, 3, 4, 5, 6 comorbidities. That's high blood pressure, diabetes, arthritis, CVD, these 2 related to cardiovascular disease. I better check what those are. So CVD, coronary heart disease and heart attack, and then overweight and obesity. So the longest item set for males is 6 chronic disease conditions, and it's these ones, okay? And in total, there are 218 different association rules relating to male chronic comorbidities for chronic diseases. Now let's look at female. So for females, first of all, there are 511 association rules. That just means that there is greater diversity in the item sets of disease conditions that females have reported. The last one, occurring in 10 individuals, is 1, 2, 3, 4, 5, 6 items long as well. So the longest item set for males was 6 on the left-hand side of the arrow. The longest item set for females is also 6 on the left-hand side of the arrow. For example, high blood pressure, diabetes, asthma, arthritis, cancer, and overweight and obesity. But look at the number of association rules where the item set length is 6. So 1, 2, 3, 4, 5, 6. So 6, an item set length of 6. 1, 2, 3, 4, 5, 6, 7, 8 association rules. Okay, you might be confused now. The point of me showing you this is that there is so much diversity in the comorbidities that females report. Okay, we have more association rules, and we have, in total, and we have more association rules at the maximum item set length for females than we do for men. So 500 association rules total for females. 8 at the longest item set. For males, 218 association rules total, only 1 at the longest item set. So if we're thinking back to what we know about comorbidities and chronic health conditions, based on our descriptive statistics, we know that men, on average, and by median, and in the histogram, they have a greater number of comorbidities. But when you're getting to more and more comorbidities, it gets to be kind of a limited set. There's only one list of comorbidities at the maximum item set length. But for females, there's so much diversity in the types of comorbidities. So even if, on average, or via the median, or by looking at the histogram, females have fewer comorbidities across the population, those females that do have comorbidities have a huge diversity of comorbidities. So they're reporting a lot of different things. And when we're thinking back to our original hypothesis of California girls will have better health than California boys, I think we have to give this association rule mining, we have to give the win to the boys on this one. Because this is simpler, right? Men are only suffering from this defined set of comorbidities. So if I'm a physician, if I'm a public health practitioner, and I want to make some recommendations for improving the health of the general male population, I know what to talk about, right? Because our association rules are more simple, there are fewer, they're more targeted. But ladies, gosh, there are so many association rules and so many different variants of them. If I'm trying to target female health, I have to cover a much broader topic set. And that's really difficult for physicians and public health practitioners to package easily digestible and generalizable best practices for health recommendations to women. So in conclusion, men have a greater number of comorbidities on average across our survey population, but women represent a much more complicated set of comorbidities. So in conclusion, as per our hypothesis that California girls will have better health than California boys, our results, based on this association rule mining on this market basket analysis, is that men win this one, because it would be easier to treat these men and to make recommendations to them than it would across all of the women in this survey. So men win. Good one for men. All right. Let me just make sure that we've covered everything in this association rule mining segment. I think that's it. So basically, it's all kind of confusing, I think. If you don't know what you're looking for, association rule mining can really be a chore. Because, just for the men, we have 200 association rules. But if you change your confidence level, if you change your support level, if you kind of start working with your data and get a feeling for what variables you're actually interested in, association rule mining, market basket analysis can be a really useful tool for generating hypotheses. And this worked out great for us since I'm not an epidemiologist, I'm not a statistician, and we didn't conduct a systematic literature review or look back at other studies to try to really define our variables of interest. So for us, market basket analysis was a great tool for us to use to kind of understand our data better and to really explore some of those more rare health conditions that we don't typically think about when we're doing more traditional epidemiological work. Okay, so we're done with this data mining exercise. I'm going to go ahead and close out R. Don't want to save the workspace image. I'll save my code, but I'll close it now. Close out this, close the snip. I'm done with the internet. All right, so that's all that I wanted to cover for this market basket analysis segment. I'm still deciding what we should explore next, but rest assured it will be interesting, and I'm going to continue to do my best to bring you some methods for exploring BRFSS data based on research that has been previously published, right? So if you feel like, Jennifer, you just did a bunch of crazy stuff, you can always look back at the articles and refer to things that other people have done. I'm just here to kind of help you explore what options are available to you when you're working with your BRFSS data. So, all right, I'll see you guys all next time. Thanks for stopping in. Bye.